Hi everyone. In the last few classes, we have discussed about spectrum of an element in a Banach algebra, representation of commutative Banach algebras and commutative C-star algebras. So from today onwards, we are going to discuss about spectrum of linear operators defined on Hilbert spaces. To start with, let us prove one important lemma. So suppose we have a dense subspace of Hilbert space H. So let D be a dense subspace of H, and we have a map T from D to H be linear and bounded. Then there exists a unique extension let us call T tilde from H to H, which is linear, bounded, and norms are same. Norm of T and norm of T hat are same. Okay, so let us call this as lemma. Okay, so first let us prove that there exists such an operator and it is well defined, and its norm is exactly equal to norm of the original operator. So the obvious choice is that we have to define T hat in such a way that T hat restricted to D is exactly T. So in other words, for every x in D, T hat x must be equal to T of x. So let us, for x in D, define T hat at x is Tx. Now when x not in D, so let us take x in H minus D. Since D is dense, we can find a sequence xn from D such that xn converges to x. So choose a sequence xn from D such that xn converges to x. Now define T hat at x is limit of Txn. We know that xn is convergent, so T is bounded, so T of xn is convergent, but we only don't know that whether T of x exists or not. In general, when x is outside D, T of x need not exist. So now T hat at x we are defining in this way. Now it is easy to check that T hat is linear. Now we want to show that it is well defined. So next is T hat is well defined. That means we want to show that the definition of T hat does not depend on the sequence that we are choosing to approximate x. So let us take that yn is another sequence which approximates x. Now as T is bounded, Tyn is convergent. Say Tyn converges to y in H. Okay, now we want to show that y equal to T hat x. So we have T hat of x minus y. So the first one is limit of txn minus the second one is limit of tyn. Okay, now this is limit of t of xn minus yn. Now we know that xn minus yn converges to 0 because both converge to the same element x. Now t is bounded, so t of xn minus yn converges to t of 0 because 0 is an element of d, so this converges to 0 as n tends to infinity. So therefore we can say that t hat x equal to y. So whatever the way, whatever the sequence you choose to approximate x, the definition of t hat x does not depend on the sequence that we are approximating. So that means t hat is well defined. Next we want to show that t hat is bounded and norm of t equal to norm of t hat. So as t hat restricted to d is t, by definition it is clear. So then we can say that norm of t is anyway less than or equal to norm of t hat because t is the restriction of t hat. Now if x is in h, then we have norm of t hat x. If you look at this is limit of txn where xn converges to x. This is norm t limit norm xn. So when x is coming from d, then anyway this is true. When x is outside d, we can approximate it by sequence xn. So where okay, from this we know that norm xn converges to norm x, so we can say that this is less than norm t times norm x. So this from this we can conclude that norm of t hat is always less than or equal to norm of t. But we have shown the other way that norm of t anyway less than or equal to norm of t hat. So hence we can say that norm of t equal to norm of t hat. Okay, so why we need this result? So if you want to define a inverse of an operator, most of the time we assume that the operator is bijective and define the inverse from the range of the operator. But sometimes even the map is 1 1, we can define an inverse. Okay, so let us take t from h to h, b1 to 1. Then we can define the inverse as a map from range of t into h this is defined as usual t inverse of tx is x for every x in h, and t of t inverse here it operates on elements of the form tx. This is nothing but this is tx. So for every x in h, that means, or we can say that t inverse y equal to y for all y in range of t. Okay, so t inverse is defined from range of t into h in this way. Now we can easily check that t inverse is linear. We don't know it is bounded or not. If t inverse is bounded, from range of t into h and range of t is dense, then it has a unique extension by the earlier lemma. So by lemma 1, t inverse has a unique extension all of h. So call this as T inverse hat. Now we can easily check that this T inverse hat is an inverse of T. Okay. Now using these two observations, the lemma 1 and this observation, we can actually classify the spectrum of a bounded linear operator into various parts. These parts are useful in finding the spectrum of an operator. Okay, so next we discuss about classification. Okay, now we know that T is bounded then T inverse is exist and it is bounded if and only if T is bijective. We can apply the inverse mapping theorem to conclude that T inverse is bijective. T inverse exists and it is bounded. So okay. Now in order to look at this bijective property, then T is bijective if and only if, so we can conclude that T is 1 to 1 and onto. Now ontoness we can write into two different parts, range is dense and range is closed. If the range is dense, now we can define the inverse operator like earlier. And if the operator is bounded on the range, then we can extend, if the inverse of the operator is bounded on the range, we can extend it to the full space to get the inverse. So that is a idea in one of the important ideas to classify the spectrum. So let us look at the, so let us take some complex number. Let lambda be a complex number. Let lambda be a complex number. Now C we can write as spectrum of T union resultant of T. Now given complex number, how to decide whether that is in spectrum of T or in resultant of T. So write down write T lambda as T minus lambda I. Now if T lambda is inverse, if T lambda is invertible, that is if T lambda is bijective, we can say that lambda is in the resultant, otherwise it is in the spectrum. Now how to check whether T lambda is bijective or not? So we can explain as follows. So we want to start with T lambda. We ask a question whether it is 1 1 or not. If it is 1 1, if the range is dense or not. If the range is dense, can we say that its inverse from the range is continuous or not? So based on these questions, we can actually describe the classify the spectrum into different smaller parts. When you actually adjoin all those parts, you get the whole spectrum. So this is the idea of classifying the spectrum. So let us try to draw a diagram where we can understand this concept. So let us start with asking the question. So we are starting with lambda in C. Now the first question we ask is, is T lambda 1 to 1. If the answer is no, then we can conclude that if T lambda is not 1 to 1, then lambda is in the spectrum anyway. So that spectrum we call as point spectrum or an eigenvalue. So we can say that lambda is in point spectrum. So in this case, null space of T minus lambda I is non-zero. That means we can find that so there exists some x, in this case x non-zero, such that Tx is lambda x. In other words, this set contains all the eigenvalues. Okay. Now suppose here if the answer is yes, then we can ask the question, is range of T lambda dense in H? So we can ask the question that is range of T lambda is dense. If the answer is no, then again T lambda is not invertible, because T lambda is 1 to 1 but range of T lambda is not dense, so it cannot be invertible. So in this case we get another spectral value, so which we call as residual spectrum. So lambda is in the residual spectrum of T. So this is called the residual spectrum. So let us see again. Lambda is in the residual spectrum means, so we have to come from the above. T lambda is 1 to 1, you should get 1 yes, and after getting 1 yes, you have to get 1 no, then we will land in the residual spectrum. In the first step, if T lambda is not 1 to 1, then we get the point spectrum or eigenvalue. Now suppose if there is a lambda such that T lambda is 1 to 1, and the second question answer yes, that is if range of T lambda is dense, then what will happen? If the range is dense, then we can ask one more question. Once we have a range, from the range we can actually define T lambda inverse from range of T lambda into H. If the range is dense, we can ask whether this map T lambda inverse continuous or bounded. If the answer is no again, so we get one more spectrum in this case. So lambda is in the continuous spectrum of T. Okay, so that means if you want to get continuous spectrum, we should get yes 2 times and no 1 time. So that means T lambda is 1 to 1, range of T lambda is dense, but the map T lambda inverse from range of T lambda into H is not continuous. Then if the answer is yes here also, that means if you have a lambda where T lambda is 1 to 1, range of T lambda is dense, and the T lambda inverse is continuous from the range of T lambda to H, then we can actually get an extension of the inverse. So in this case, so lambda will be in the resolvent set. Okay, so this is the resolvent set. Because we can use the earlier lemma that T lambda inverse can be extended to the full space uniquely, and this serves as an inverse of T lambda. Is the inverse of T lambda. Okay, so this is the classification of spectrum. We can actually write down the spectrum of T as the point spectrum of T union the residual spectrum of T union the continuous spectrum of T. So here this is disjoint union of sets. Now using this small parts of spectrum, we can actually get the full spectrum using by taking the union of all these sets. Okay, so let us again write down the definition of each spectrum. The first one is the point spectrum. So this is sigma pt is set of all lambda in C such that T lambda is not 1 to 1. So in other words, we can write set of all lambda in C such that null space of T minus lambda I is non-zero. This is set of all eigenvalues. Okay. The second one is the residual spectrum. This is sigma suffix r of T is set of all lambda in C. So we will get one yes and one no. From the first question will come to the next level. That means is range of T lambda equal to h. We ask the question. When we get no as an answer, we get lambda in the residual spectrum. That means T lambda is 1 to 1, but range is not dense. So this is T minus lambda I is not 1 to 1. Sorry, this is 1 to 1. This is 1 to 1, but range is not dense. Okay, the next is the continuous spectrum. Okay, this can be defined as sigma CT, set of all lambda in C. So when we want to get the continuous spectrum, we should get 2 yes and 1 no. That means T lambda is 1 to 1, range of T lambda is dense, but the inverse is not continuous. So T minus lambda is 1 to 1. Range of T lambda is dense, but T minus lambda inverse is not continuous. Okay, so this is one way of classifying the spectrum. Of course, there are different ways. We will be looking at other classification of the spectrum at a later stage. Okay, now let us try to look at a few examples to see how to get the spectrum. So let us look at define T from C2 into C2 by T of x1 x2 as lambda 1 x1 lambda 2 x2 for all x1 x2 are coming from C2. So here lambda 1 lambda 2 are fixed complex numbers. In other words, with the standard orthogonal basis of C2, the matrix of T is given by this diagonal matrix with diagonal entries as lambda 1 and lambda 2. Now we know that the set of all eigenvalues here is lambda 1 lambda 2. So hence we can say that point spectrum, in fact we can show that the set of all eigenvalues is exactly lambda 1 lambda 2. So in this case, in fact if you take any lambda which is not equal to lambda 1 and lambda 2, you can say that T minus lambda is invertible. That means we can conclude that the point spectrum and spectrum are same, and in this case we can conclude that the residual spectrum is empty and the continuous spectrum is also empty. So the reason is that if T lambda is 1 to 1, if it is not 1 to 1, it is not onto, and in this case range of T lambda I is a finite dimensional space. So it is it may be one dimensional or it may be two dimensional, but actually we can say that range of when you take lambda which is not equal to lambda 1 lambda 2, then we can say that range of T lambda is exactly full space. So for that reason we will not get the residual spectrum as well as continuous spectrum. Okay, so this can be generalized for any n by n diagonal matrix. And we also have an observation earlier that if dimension of H is, let us say, n, which is finite, and T be a linear operator or bounded, then we can say that point spectrum of T is exactly the spectrum of T. Okay, because here T minus lambda is 1 1 is equal to the fact that it's also onto. From that we can conclude that the residual spectrum and the continuous spectrum are empty, so we can get this result. Okay, now let us look at an infinite dimensional case. So let us take lambda n from L infinity and define L2 into L2 by T of x1 x2 x3 is lambda 1 x1 so this is T of xn, we can take as lambda n xn for every xn in L2. So this is the diagonal operator that we have seen earlier, that the matrix of T with respect to the standard or the null basis is exactly the infinite matrix with diagonal entries as G lambda 1 lambda 2 lambda 3 so on. So we have observed that this is a normal operator. We want to see the spectrum of T. So earlier case the spectrum of T is exactly the diagonal entries, but here when we have a sequence, then we also have to include the limits of the sequence because we know that spectrum is closed. So for that reason in this case we can actually show that the spectrum is set of all lambda n, and union their limit points. So here the claim is the following. Here bar is nothing but the closure of the set, not the conjugate bar. It is the closure of the set. Okay, so one thing is clear that T of En is lambda n En for every n in n, where En is the standard orthogonal basis for L2. So this implies that this set lambda n is in the point spectrum for every n in n. Now we want to show that the closure of the point spectrum is exactly closure of lambda n in n. Okay. So let us take lambda, which is not lambda is a point in the point spectrum. So then there exist x equal to xn in L2 such that Tx equal to lambda x. So that is, we can say that T of x1, x2, x3, so on is lambda 1 x1, lambda 2 x2, lambda 3 x3, so on. Or we can write this as, so this again equal to this equal to lambda x, so this is lambda x1, lambda x2, so this implies lambda minus lambda j into xj is 0 for every j in n. Now x is non-zero implies there exists some j in n such that xj is non-zero, at least one component is non-zero. Then in that case, so from this equation, let us say star, so we get that lambda equal to that particular lambda j. So if lambda is any arbitrary eigenvalue, then it has to coincide one of the diagonal entries. So the conclusion is the following, that point spectrum of T is exactly set of all diagonal entries. Okay. Now spectrum is closed, so therefore we can say that point spectrum of T closure is also contained in spectrum of T, because spectrum is closed. You can take the closure both sides. Okay, now the claim is the following: spectrum of T is exactly point spectrum of T closure. Okay, let us take lambda, which is in the spectrum of T but not in the closure of the point spectrum. Then we can say that the distance between, let's say distance between lambda and point spectrum of T closure, this is positive because the closure of the point spectrum of T is a closed set, so this distance is bigger than 0. Now for any x in H, in this case L2, we have, if you look at norm of T minus lambda I square acting on x at square, the square of norm of T minus lambda ix. If you compute this, so this is now Tx we can actually write down. So our idea is to show that lambda cannot be inside the spectrum at all. Now lambda is outside the point spectrum of T closure, we show that it's also outside the spectrum. So from that we can conclude that the spectrums are same. That means that these two sets of spectrum of T and the closure of point spectrum are same. So for x in L2 we can write x as summation n equal to 1 to infinity inner product x en with en, and from this we can say that t of x summation n equal to 1 to infinity inner product x en with en. Okay, so we want to look at t minus lambda ix. This is summation n equal to 1 to infinity lambda n minus lambda inner product x en multiplied by en. So we can actually look at the square of this one. We can using the orthogonality of en, so we can conclude that this is summation n equal to 1 to infinity mod lambda n minus lambda square inner norm of inner product of x en square modulus of that. Okay, so this can be done easily. Okay, now we know that the distance between lambda and lambda n is bigger than or equal to d, so we can say this is d square summation n equal to 1 to infinity inner product x en square modulus. So this is d square x square. So therefore we can say that t minus lambda is bounded below. That means range of t minus lambda is closed. It is also 1 to 1. So to show that t minus lambda is invertible, it is enough to show that range of t lambda is dense. So claim range of t minus lambda is dense in H. Here H is nothing but L2. But what is range of t minus lambda I? We have range of t minus lambda I closure is exactly null space of adjoint of this whole operator t minus lambda I, that is null space of t star minus lambda bar I. Now what is t star? So t star of y1, y2, y3, we have already seen that this is exactly lambda 1 bar y1, lambda 2 bar y2, lambda 3 bar y3, so on. Now t star minus lambda bar I at this y1, y2, y3, this is lambda 1 bar minus lambda bar y1, comma lambda 2 bar minus lambda bar y2, so on. Now we can show that null space of t star minus lambda bar I so this we can show this to be 0. The reason is that if you look at the definition, so if the right hand side of the above equation is 0, means lambda I and lambda is not equal to any of the lambda i's, so from that we can conclude that each yi is 0. So from that we can easily say that null space of t star minus lambda bar I is 0. So here if we go back, this is orthogonal complement and this is exactly 0 complement, and that is H. So we can conclude that range of t minus lambda is dense. But we have already shown that range of t minus lambda is closed. So from these two we can conclude that range of t lambda is full space, and we already know that t minus lambda is 1 to 1. So what we have shown is that when we take lambda outside the closure of the point spectrum, we have shown that t minus lambda is bijective. Now from the inverse mapping theorem we can conclude that t minus lambda I inverse is bounded. So therefore lambda is inside resolvent of t. So whenever we have taken lambda outside spectrum of t closure, but in the spectrum, so if Okay. So when we have taken here lambda in the spectrum of T but not in the closure of point spectrum, that means we assume that point spectrum of T closure is proper subset of spectrum of T. Then we got that lambda is in row of T, but we already know that lambda is in the spectrum of T. So this is a contradiction. So hence we can conclude that therefore point spectrum of T closure is exactly spectrum of T. Okay, so let us again come back to the example. So in this case we have shown that spectrum of T is exactly the closure of the diagonal entries. So as a particular case, let us look at the following operator. Define D from L2 into L2 by D of En is mapped to 1 by n En, where En is the standard orthogonal basis of L2. Now with respect to the standard orthogonal basis, we can actually write down the matrix of this D. It is nothing but the diagonal operator with diagonal entries 1, 1 by 2, 1 by 3, so on. And in this case, spectrum of D is point spectrum of D closure, that is set of all 1 by n, n in n, closure of this set. So this is 1 by n, n in n, and it has only unique limit point, namely 0. So this is the spectrum. This operator we will be using again and again at a later stage. Okay. In the next class we discuss few more examples and one more way of classifying the spectrum, which is useful in finding the spectrum of an operator. Note that this classification of the spectrum, whatever we have defined earlier, is available only for operators, not for arbitrary elements in a abstract Banach algebra or sister algebra. Okay, I'll stop here. Thank you very much.